Hi everyone, Ryan Duffy back here again, Ruminant Technical Manager with Precision Microbes. I'm back for another installment of Tech in 10, where we'll be diving into the science of oral fluid therapy. Matthias, you're going to give me 10 minutes, so I'm going to have 10 minutes to discuss a technical topic. And this week we've decided to focus in on the very science of solute-linked water transport. How do we get fluid from the lumen of the gut across the gut lining and into a calf that is experiencing neonatal calf enteritis? So in the first installment, where we focused in on Hydro-STIM, we have ended up with quite an electrolyte-rich fluid, which has now been administered and it's going along the lumen of the gut. Here we have our lovely gastrointestinal mucosal enterocytes, so the very cells that are responsible for the absorption of nutrients and water across the gut lining and into the systemic circulation. So we have electrolyte-rich fluids. I'm talking about solute-linked water transport and the relevance Hydro-STIM has in this. So Hydro-STIM is actually known as a hyperosmolar oral electrolyte solution. And the reason for that is it has quite a number of particles actually in it, or solutes in it. The reason that that's actually been included is because we're trying to really exploit solute-linked water transport. And specifically, how are we doing that? We're doing that with glucose or dextrose, glycine, which is a neutral amino acid, and a glycogenic amino acid, but also certain organic acids such as acetate and citrate. So the likes of these, which will also help with solute-linked water transport. Now, while this electrolyte-rich fluid is coming down here with these solutes, we have a number of surface receptors which are responsible for helping with the absorption here. Now, naturally enough, the initial reaction would be, if we're putting in something that's quite concentrated, it will actually draw fluid out of the gut and out of the body and into the gut itself. But what we're doing here is we're trying to get water across by the action of these receptors. So you'll see here I have SGLT1, which is sodium glucose linked transporter 1, and it's there on the luminal surface of these enterocytes. Now, what exactly does this receptor do, particularly whenever we're talking about solute-linked water transport? Well, it will take 2 sodium molecules and it will take 1 glucose molecule. It will absorb both of them into the enterocyte. Now, with that, it will take fluid with it also. So therefore, we're actually helping with the rehydration. So even though initially there may be a little bit of lost fluid, it is quickly reabsorbed as a consequence of that. That is because the product is going from hyperosmolar and it's being reduced down in respect to its osmolality with this absorptive process. So the likelihood of fluid actually being lost is going down as time progresses. Now, once glucose and sodium has entered the cell, sodium will come to the basolateral membrane, and with there it will function with the sodium potassium ATPase, which will take 3 sodiums out of the cell and put in 2 potassiums. Essentially, that's the right level of electrolytes we want. We want higher concentrations of potassium intracellularly, and we want more sodium extracellularly, particularly in the interstitial fluid. And I'll tell you why that is exactly the case. Sodium is referred to as the osmotic skeleton of the extracellular fluid. Essentially, the concentrations of it, its location, determines where fluid balance lies. So if we have lots of sodium within the circulation, within the interstitial fluid, within the extracellular fluid, we're going to have more fluid going that direction. And that's going transcellularly, but also through tight junctions between enterocytes. So we're getting lots and lots of fluid back into the body. What happens to glucose? Now glucose, which is intracellularly, goes to this basolateral receptor, the GLUT2 receptor, and that allows it to be absorbed into the body. So that's essentially what's happening there. Now, I'm only focusing on glucose, but mind you, we have other solutes in here. We have glycine, we have organic acids, as we've mentioned before, acetate, propionate, which use other processes, not just SGLT1. So we have multiple means of getting fluid transcellularly and paracellularly, so the calves will rehydrate efficiently, whilst providing them with energy, whilst providing them with key tier 1 electrolytes. So it's going to enhance recovery. Now it comes down to the right concentration. It's getting this right. So this is where I'm going to talk about the glucogenic source to sodium ratio. This is essential if we're talking about proper recovery in calves. If we have a glucogenic source to sodium ratio of less than 1:1, we're not providing enough of an osmotic gradient to get sodium or water across transcellularly or paracellularly. We will not rehydrate the calf. If we go over 3:1, the problem is we're providing too much dextrose. We already know there's dysbiosis in here, and that dysbiotic state is resulting in metabolic acidosis. So the last thing we want to do is feed these pathogenic microorganisms which are causing the dysbiosis. So over 3:1, we can actually induce an osmotic diarrhea. We want to avoid that. Now, where does Hydro-STIM come into the equation? Well, Hydro-STIM has a glucogenic source to sodium ratio of 1.9:1. So it's right there in that sweet spot between 1:1 and 3:1. It has been specifically tailored for that concentration so that we can maximize solute-linked water transport without posing a risk of osmotic diarrhea. So that is the science of oral fluid therapy in respect to solute-linked water transport, the role that hyperosmolar fluids actually have in respect to treating neonatal calf enteritis. If anyone has any other questions, please do not hesitate to ask us. We're very, very keen on going through oral fluid therapy and the relevance Hydro-STIM has in calf recovery.